what it is. A is 1. Okay, so everyone see that there's a 1 in front of all these? Okay, so A is 1. And what's R? 1/2. And is the absolute value of R less than 1? Yes. So the absolute value of R here equals the absolute value of 1/2. Which is less than 1. Therefore, I'll say thus, the series converges, right? But because it's geometric and it converges, we can actually find the sum. The sum is going to be A over 1 minus R. So this sum is going to be A1 over 1 minus 1/2, which is 1 over 1/2, which is 2. Now, let's actually have the computer verify that for us. We're gonna go to type this in here. This was 1/2 raised to the n minus 1. There you go. Well. So take a look at this. The sequence was going to 0, right? If it went somewhere other than 0, then it would have had to have diverged, right? So this went to 0, and then look at this sum here. I've gone out 15 terms. Let me go out. Man, it converged very fast, didn't it? Look at how flat that is. Man, let me go back. Okay, there we go. Like the fourth term, I'm at 1.86, right? Fifth, like I get to 2 really quickly here, don't I? Now, the computer is actually rounding this. I don't know how many decimals. Let me see. I don't know how many decimals I have this to. Round sum. Let me make this. It was 1/2 raised to the n minus 1. Okay, so I increased the precision here of this. So you can see here, I'm out 10. Let's see, 11. Whoa, no, I'm hitting the wrong button. Okay, there we go. So look at this number here, 1.99. I'm 15 terms out, 1.9. Look at that. At the 20th term, I'm out 1.9999. So what's this? Tenths, hundredths, thousandths, 10,000, 100,000ths, right? So I'm within 1/100,000th of 2 after going out and adding up the first 18 terms. Let's go even more. Where was that?
How come the sequence is listed as 2 to the end?
The computer is smarter than us. It's just rewrote it. But that's a great question. It's written 2 to the 1 minus n, right? Yeah. Which is the same as 2 to the negative n minus 1. So if I factor a negative out of both of those, I get this, right? Yeah. And then that's the same as 2 to the negative 1 to the n minus 1. And then 2 to the negative 1 is the same as 1/2 to the n minus 1. Don't worry, I'm glad you asked that question. The reason I'm showing it to you is because we're going to actually have to do this in a little while. Okay? All right, so, whoa, what happened? Oh, I'm in the code. Okay, so, why am I not going out more decimal places here? I'm looking at it. Locator, row, round. Well, let me keep going here. That's not important. Okay, does this make sense? All right. How about this one? Sum n equals 1 to infinity of 1/2 to the n. So what are you thinking? Does that look geometric to you? No? Well, why not? It doesn't have n minus 1, right? Doesn't have n minus 1. If it had n minus 1, it would be really nice, right? Because then I think we'd be in business, right? If it had that. It does have that, doesn't it? Isn't that n minus 1 plus 1? We've done this before, right? And we didn't like it. Well, we liked it, but we didn't like it. Is that the same thing? Okay, so I'm trying to force an n minus 1 in right now. So this is the same as sum n equals 1 to infinity. Now, I'm really looking at this as two different exponents. I'm going to rewrite that as 1/2 to the n minus 1, and then times 1/2 to the 1, right? Because that would be same base, different exponents, multiply together, you add these, right? Yeah. So this is this, and then I'm going to rewrite that as 1/2 out front, then 1/2 to the n minus 1. Now does that look geometric? Yes? So this is geometric now. You could pull this sum out, but in the formula we need an a, right? But yes, you can. You could pull this out. You just have to leave it out there. I'm going to use it in there. So this is a is a half, right? R is a half. And since the absolute value of r is again less than 1, this converges. What does it converge to? A over 1 minus r. A over 1 minus r. So the absolute value of r is less than 1, so it converges. So what is that? It's 1. It's a different sum, isn't it? It's a different sum than the last one. And the reason why is because, like, if we plug in 1 here, what do we get? If we plug in 1, what do we get? A half, and then you say a half plus, the next one would be, plug in 2, a fourth. So it would be a half plus a fourth plus an eighth plus a 16th, right? But the previous one, when we plugged in 1, we got 1. Then 1/2, then 1/4. So they're two different things. Now I wanted to show you this one because I can remember this. I think I was in 6th grade when my science teacher posed this question to us. That's the sum, isn't it? That's the sum that we're looking at right now. And we're saying it what? Converges to 1. So this question, I can remember distinctly the room I was in and the teacher. We were all facing that way in the room, and she said, okay, what I'm going to do is I'm going to start on this side of the room, okay, and then I'm going to walk halfway across the room, right? Okay, so I'm halfway there, right? And I'm going to walk a fourth of the way. So if the whole room, we say that that's 1, right? Then this would be half. Then if I walk a fourth of the length of the room, that would take me here, right? Then if I walk an eighth of the length of the room, that would take me halfway there. Right, so I keep on going halfway, halfway, halfway. So do I ever reach the wall? Yeah, I mean, do you ever reach the wall? If you go half and then half of that and then half of that and half of that, what is this telling us happens? This sum, right, which is half, 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 does what? Converges to 1. Does that mean it ever gets to 1? No. Just means that it's headed towards 1, right? If you could do that forever, you would reach, but you can't do it forever, right? So this leads to something called, there's different versions of this. There's something called Zeno's paradox. You may have heard of this before. But it says that a runner can never finish a race. Because to finish a race, the runner would first have to go half the distance of the race, and then have to go half of that distance, and then half of that distance. And that infinite sum, right, converges, but it never gets there. So a runner can't finish a race. But we know a runner can finish a race, right? So the convergence, it does head to, I don't know, it's a paradox because you can argue it, but we know you finish, right?
So just never run in real.
Right, I mean, think about it. Doesn't it take, if I go half the distance, that took me some time, didn't it? Then if I go half that distance, that took me some time. Then I have to go half of that distance, that took me some time. And I have to keep doing those halves the whole way. And each one of those halves is going to take me time. So it should take me an infinite amount of time to reach the finish line because I have an infinite amount of halves to do. That's a paradox because we know you finished the race, right? So that's what a paradox is. It's kind of like counterintuitive. Okay. Y'all doing all right with this so far? If it's not geometric, what? Oh, if it's only geometric. Sorry. Okay, so on your sheets, do y'all see that geometric is the second one listed? And can you understand what it's saying now that you read through that? You have a series, it has a special shape to it, right? It looks like sum, blah, blah, blah. And then it says converges to this actual sum S. Now, look, I want you to add something to this sheet. Do you see where it has the geometric right here? Written like this. Right above it, or below it, well, probably above it, I want you to write this. And let me write it down first before you write it. Ooh, I've done something different here. These are both geometric series. Now let's see why. Notice that I've changed my index. You know how I started here at 1? We've been starting at 1 the whole time, haven't we? It turns out as we proceed that you can start your index anywhere you want. And if we choose to start it at 0, what would happen? So this is what I want you to write there, and that's it. But I want us to compare these two. What would happen if I plug 0 into this? I get, what's the first thing I get? A. And then when I plug in 1, I get AR. And then the next one, AR squared. You see that? But that's exactly what this gives you, right? So this gives you A plus AR plus. So these are the exact same things. So by changing the index from 1 to 0 and changing n minus 1 to n, you create this same exact series. So with geometric, if you see it like this or this, they both give you the same thing, all right? Now, let's do another one. Let's do 5. Let's go 5 to the n plus 2 over 7 to the n minus 3. So as we start to look at these series, we want to start to see like that it's geometric. So how are we going to determine that a series is geometric? The main key, I guess, is the fact that you see your index n. Do you see how the n appears in the exponents? That's what leads you to think geometric. If you've got a base that's a number raised to your variable, which is your index, then that's like an exponential function. And geometric series are basically like exponential functions. All right? You always have that r to the n. So what we're trying to do is see if we can make that look like this. Can we make that, force it to look like that? Okay, how? How do you mean multiply them?
Isn't that the same as just 7 over 1 and doing like 1/7 to the n minus 3?
Oh, you mean like slide that to the side and write it as 1/7? Yeah, we could do that.
and then multiply the exponent, or not multiplying, but whenever you're multiplying the exponents add.
They have to have the same base,
Oh, okay.
right? You have to add exponents. You have to have the same base, and they would have one base would be 5 and the other would be 1/7. So that couldn't go together. So what I think you should be focusing on is the fact that we need to find some number r raised to the n minus 1, right? You ready? You tell me. What else do I need up there in that exponent? N minus 1, then what? Plus 3. You don't quite need the plus 3, minus 3, because look, what's minus 1 plus 3? 2, right? So isn't that a nice way of writing that? Okay. And then how could I rewrite the 7? N minus 1 minus 2. So do you see how I've forced an n minus 1 into both of the exponents, right? Now what I'm going to do is I'm going to split these up. So I'm going to write 5 to the n minus 1 times 5 to what power? The third, right? That's basically splitting this right here. And on the bottom, I'm going to do 7 to the n minus 1 times 7 to the negative 2, right? So that's splitting this one right there. Is that all right? Now this is just 5/7 to the n minus 1. Now the reason I can do that is just properties of exponents. If you have something to a power over something to a power and those are the same powers, then you can put these two as a fraction together to the same power. So this would go to both of these, right? So I'm kind of reversing the property of exponents, but I still have some more stuff, right? Yeah, so this 7 to the negative 2 really comes up as 7 squared. And so I really have, like next to this, 7 squared times 5 cubed. 5 cubed is 125, right? 7 squared is 49. So somebody, please, if you don't mind, 49 times 125? 6,125. You'll see what I've done? So I put those together and I moved it out front because that's my A, isn't it? That's my A. So let me just identify now. This is geometric. This has got an A of 6,125. And the R here for us is 5/7. And of course, the absolute value of R is less than 1, right? And that means it converges. And what does it converge to? Yeah, so just do the formula. A over 1 minus R. A over 1 minus R, right? That's it? So I'm just going to put that answer right here. A is 6125 over 1 minus R, but R is 5/7. So what's 1 minus 5/7? 2/7? Flip it, all right? So flip this. When you flip, the 7 goes up on top, and the 2 just stays on the bottom, right? And I'm going to leave it as a fraction. I'm not going to do a decimal on my calculator. So what is, if someone could do that, do this times 7. 42875 over 2, right? That's it. Is that okay? I don't know. Go. You have who has that right there? Go ahead and give. What's the decimal for that? Can you tell me? Like, go ahead and get that.
21,437.
21,000.
437.
Okay.
0.5.
Point
5.
5. Okay. Yeah, that's what that adds up to be.
It's not even a year's salary.
Okay. There we go. So you're going to need to be able to manipulate these series, right, to make them look geometric. Now, we're going to do something that's kind of, I think this is kind of interesting. Let's take a look at that decimal, 0.35353535 repeated forever. That's what that bar means, right? That goes forever. Now, did we talk at all about rational versus irrational numbers? What's the big difference between irrational and irrational? What distinguishes these two types of numbers? All rational numbers, can, when they're written in decimal form, either stop or have a repeating pattern. So like a rational number like 3/4 is 0.75, right? A rational number like 2 is 2.0000, right? Repeating pattern, 000 forever. A rational number 1/3 is 0.333 forever, right? Repeating pattern. Versus pi, which is approximately 3.1415. And see, the problem with this is that this keeps going, but there's no pattern to the repetition. Right? There's no pattern, it just keeps changing randomly almost. All right? So if you have a repeating decimal or a terminating decimal, then it must be a fraction. So my question to you is, what's that fraction? Because that repeats, right? So that is a rational number. What is the fraction for that number? Do you have a function on your calculator that does that? Maybe. No, don't look for it. Don't look for it. I don't care if you do. You ready? Watch this. Watch me. Do you agree with this? Do you agree that that's equal to 3/10 plus 5/100 plus 3/1000 plus 5/10,000 plus 3/100,000 plus 5, I think I'm at million now. Let me see. 2, 3, 4, 5, 6. Do y'all agree with that? Right? Because this is what it means. This is what the decimal means. 3/10, 3/10, 5/100, 3/1000, and so on and so forth. Yeah? Now, because my repeating pattern is 3, 5, 3, 5, 3, 5, I'd like for us to put these two together, these two together, these two together, and let's see what we would get. You would have to do a common denominator here, right? Yeah. So multiply top and bottom of this one by 10. So you get 30 plus 5, which is 35, over 100. Okay? What would the next one be? 35 over 100 plus 35 over 10,000, right? Plus 35 over a million, plus, and that pattern continues. By the way, there's homework problems like this, so just letting you know that. I said let's look at something kind of interesting, but this is something that I would test you on also, all right? So I'm not doing this just for fun. Okay, so you see this? Now watch. See if you agree with this. 35 times 1/100th plus 35. Do I want to do it this way? You know what? Hold on. I'm not going to do it that way. Let's do it this way. 35 over 10 squared plus 35 over 10 to what power? Fourth power plus 35 over 10 to the sixth. We have a pattern here, don't we? 35 is always the top, and the bottom is always 10 to an even number. We know how to generate even numbers with formulas, don't we? So can I write this in sigma notation? Can I rewrite this using sum n equals 1 to infinity 35 is always on top, and then on the bottom you need 10 to even numbers. So what's the formula for even numbers if we want to start at 2? So 10 to the 2n, right? I claim that that's a geometric series. How can we make that look geometric? 35 is kind of like that A out there on the side. Okay, so let me try that. Since the 35 doesn't change, let's do 35 out here times, now the 10 is on the bottom, isn't it? I'm going to rewrite that as 1/10 to the 2n. Wouldn't that generate the same exact thing? Because 1 to any power is 1, and on the bottom, 10 to the 2n would be on the bottom. So this is this, yes? Now we have a problem. What's the problem? Because this is not geometric yet. What's our issue? We need that to be to the n minus 1, right? And I can't just do minus 1 plus 1 right now because I have 2n, don't I? So here's one way I could resolve that. How about 1/10 squared to the n? Isn't that the same as 1/10 to the 2n means 1/10 to the 2, right, squared, and then to the n, because you multiply those and you get 2n. But what's 1/10 squared? 1/100th? You follow that? This is just exponent properties here. Yep, then I'm going to do the n plus 1 minus 1 after that. So this is going to become 35 times 1/100th to the n. So I just did 1/10 times 1/10 is 1/100th. And now I'm going to do the minus 1 plus 1. So can I do it this way? Watch. Can I do this? Minus 1. And instead of me doing plus 1, can I just do this? Is that all right with you all if I do that? That's the same thing as doing the minus 1 plus 1, right? And that 1/100th can come out here and be friends with the 35, can't it? 35 over 100, 1/100th to the n minus 1. That is a geometric series. A is 35 over 100, and R is 1/100th, which the absolute value of that's less than 1, definitely, right? So this converges. What does it converge to? A, so A is 35 over 100, over 1 minus R, which is 1/100th. Bless you. And what happens if you do that? Bless you. Yeah, get it together over there, please. 35 over 100. You might be allergic to series. What is that, 99 over 100 on the bottom? And look what happens when you flip that.
Hundreds canceled.
The hundredths cancel, and you're left with 35 over 99. Someone on their calculator, please type in 35 divided by 99. And pardon? What do you mean top number? Like this 35? It's this, yeah, so it's that divided by 99, and you get that. What? Yes?
Why did you do 1 over 100 in purple?
Well, okay, so from this step to this step in the black is just rewriting the 1/10 squared, right?
Okay.
But then to make it geometric, I need that to be a -1. So I did -1 plus 1, but I just peeled this one off already. I didn't feel like writing that. So what I did is I already split it, and I did this one here, and then that one would be here. Make sense? Okay. So that's it, right? This is the rational number that gives you 0.353535. So it actually turns out that this works for any repeating decimal. It's kind of nice. So check this out. Just give me a guess as to what you think 0.444 repeated is. 4/9. It's just 4/9. If you type into your calculator 4/9, because 4 just keeps repeating, right? 4, 4, 4, 4, 4. Now what if I did 42 repeated? 42 over 99. You can check it for yourself. What if I did 512 repeated? 512 over 999. Okay, that's what happens, all right? Now, this leads to something really crazy. What's 0.99, repeated? Yeah, we did talk about this, right? If you're going to follow this formula, right, what would it be? It'd be 9 over 9, right, which would be 1. And I did talk about that in class, right? Was it a week or two ago? That there is no number between 0.99 and 1? That 0.99 is 1. It's convergence, though. This is the thing. What you actually have here is you have 9/10 plus 9/100 plus 9/1000, right? That's what's happening here. And so when you look at this as a geometric series, you're adding, and this is converging out to 1. If you could go forever, it's converging to 1. Yes?
Is that kind of like the example you gave with the jogger that never finishes the race?
Yep.
It's like,
Yep, you could do this. I have to walk 9/10 of the way, and then 9/100 of the way, and then 9/1000, right? And eventually it converges out to 1. The thing is, the reason why you have to say that this number is 1 is because you can't find a number between them. Look, do you agree with this statement? That let's say I have a number line. Let's say that I have two numbers, x and y. Let's say those two numbers are different numbers. They are not the same numbers. I can always find a number in between them, always, by just taking their average. Always. You can do it with a specific example. If you have 4 and you have 6, how do I find the number right between them? I add them up and I divide by 2, right? And I would get the number 5. So if you have two distinct numbers, you can always average them to get the number in between. If you take these two numbers, okay, and you say they're different, and try and add them and average them, what are you going to get? What would you get? So think about it. If I say, hey, what's the number between 4 and 4? Then what would you do? You would add 4 and 4 together and divide by 2, and you would get what? 4, right? So if you take these two, add them, and average them, you're going to get 1 again, which means they're the same number. Okay. You don't believe it? It's all right. Now, there is something much more difficult than what I just gave you. Something like this. So what do you think 0.1232323 would be? You see the difference between this one? You see the 0.1 there? Then it goes 232323. That is not 23 over 999 or 99 or anything like that.
110 plus 23 over 99.
I actually not quite sure exactly what this one would be because it's not as clean as the other one. You'd actually have to do it. So in your homework there is going to be a problem like this. So what I suggest you do is just start writing it out. So let's do this. What would it be? This is 1/10, right? And then this would be 2 100ths. Can I just do this right now? 23 thousandths. Basically what I'm doing is I'm saying it's going to be 23, and then this is the thousandths position, right? And then that would be the same as me doing 2 over 100 and 3 over 1,000 and then combining them together with a common denominator. And then what would my next one be? 23 over, how many zeros do I need to add? 2 more. Okay? Now, this here all the way down is geometric. And you'll be able to come up with the formula for this and do all your, play your game, and this will turn out to 1a over 1 minus r, okay? And you will get an answer. But then out in front of it, you have to do what? Add 1/10. So this is going to come out to be a fraction, right? A over 1 minus r. Then take that and add 1/10, which means you have to get a common denominator and put them together, and that will be your answer, okay? See if you can handle that. I do it, of course, in the homework solution videos, but all right. Now, we have 5 minutes. We have to talk about a test, and harmonic, I guess we can not worry about harmonic, because harmonic's going to take us like 5 minutes to do. It's really not, I just show you, hey, look, it diverges always. So let's talk about the test, because that's probably the most pressing issue in your mind right now. I've started to put the test together. I started it last week, and last Friday I started working on it. I got through about half of it, and then I said, that's it for now. So I haven't touched it since then. But I do have a little kind of review for you. Not to hand out, sorry. I'm going to show it on the board. I hope I'm right when I say that I feel like this test is going to go well. Because I feel like the test is not really trying to throw you off or confuse you. It's just very straightforward. All right, so here's what you should expect. Your test is not Tuesday, your test is Wednesday. This was for my other class. I showed this to them. So you need to be able to set up, and I stress, set up. A lot of you on the take-home worked your integrals all the way out, and I mean, good for you. Good for you. But you didn't have to, and that's exactly what I want you to do on the test. Just set up the integral. You don't even need to expand things out. Just if it's this function squared minus this function squared, just put the functions in parentheses and be done. Okay? It's supposed to be fast. What I want you investing your time in is giving me good drawings that show detail as far as, like where things are, where they intercept. So, be able to set up the following integrals. Area between curves. So I give you 2 curves. You have to find the area between them. And that means you're going to have to find intersections. On the take-home also, I took off points if you found the points of intersection without showing me how you got the points of intersection. So you had to algebraically work that out. And the one on the take-home, I believe, was like a radical equation. You had to square both sides and solve, and it turned out to be, it was a nice polynomial. It worked out nice. But same thing on the test. I want you to demonstrate that you can do some algebra to get the solution, or to get the intersections. And then when it comes to this, it could be, when you do the area, remember it's f minus g, right? Top minus bottom. Unless they're functions of y, and then it would be like the right minus the left. So you need to be comfortable with your functions either being functions of x or y, and be able to work with those. And then we do the volumes. So pretty much like the take-home, I'm going to want you to be able to take a region and wrap it around different axes. There were 6 different things that could happen. I'm not going to do all 6 on the test, just for time's sake. And you must be able to use shells. I did also notice on the take-home exam that, my take-home quiz, that on problems, what is it, 5, 6, and 7? Was it 5, 6, and 7? Those, I was hoping you would use shells on, but some people were insistent on using the washers, and so they solved those equations for x. Well, it turned out that they could be solved pretty easily. But it was more luck than anything else, because What was one of the functions? It was y equals x squared minus 2x plus 1? And the other one was what? 4 what? 4 root x? Okay, yeah. So to solve this one for x, you just move the 1 over, divide by 4, square both sides. For this one, you get really lucky because the right-hand side is x minus 1 squared. So you can take the square root on both sides and then add 1. On the exam, I'm going to give you curves that you cannot solve for x, all right? You will not be able to solve for x. So you're going to be forced to use shells. I just want you to make sure you're comfortable with it, all right? And then I'm going to ask you to find a formula, okay? So, well, I say find the volume, but remember, this all lies under setup only. Find the volume of a solid with the base formed by a region between two curves and cross sections perpendicular to the x-axis forming either squares, semicircles, triangles, etc., etc. Right? So one of those. And then find length of the curve. Oh, yeah, okay, so look, you see this find length of curve, surface area of curve? I've decided I'm not going to put these on the test, and I'm going to give you some sort of take-home for this. Okay? For these. So that's really going to dramatically reduce the amount of material you have to know for the test. So no length, no arc length, no surface area on the test. Expect a take-home assignment for that. Clear? Okay, I give you a sequence. I give you some sequence. You give me the formula. Okay, so like, oh, how do I generate even numbers, right? Oh, these are all powers of 4. We went around and did that. Was it this class where we were around? Yeah, okay, so, all right, now, finding the limit of a sequence. That was a homework assignment. You might need to use L'Hopital's rule. Remember, on this test, if you're going to use L'Hopital, you need to switch it to a function of x. And then do your L'Hopital and then go back and give me your result. All right? Or you also might need the squeeze theorem. And then this last one,
Wait, I'm sorry, what did you just say?
you might need the squeeze theorem.
No, like, you can't do L'Hopital if it's like a y?
No,
You have to make it a function of x. So like if I give you, on this test, if I give you the sequence n over n plus 1, I ask you what its limit is, you have to first say, okay, I'm going to look at this as a function of x, and then I'm going to use L'Hopital, and then get that answer, and then you can say this is 1. Okay? So I want you to know that we're switching out. Now this last part, this will be probably a bonus on the test. Okay? Everyone's like, how can I improve my grade? And oh, can I do? Be ready to do a bonus where I give. So this was the one where you have to like really logically put down your steps. I show you, or I ask you to use the bounded monotonic sequence theorem to show a sequence converges, which means you have to show what two things? It's bounded and it's monotonic, right? So bounded means you have to find a capital M that's always bigger than your sequence, and a small m that's always lower than your sequence. That's how you show bounded. And then monotonic was one of two inequalities you have to show. A sub n is less than a sub n plus 1, or a sub n is greater than a sub n plus 1. Yes?
So when we get the take-home assignment, will that be Wednesday as well, or would that be the one?
I'm thinking the take-home assignment I'll give you on Wednesday. Here's the problem with that take-home assignment. I don't believe I'm going to have that grade put into the system before the drop date. And the drop date is this Friday, I believe. So if anyone's like, concerned, I will have your exams graded and not back to you, but I will have them graded and posted in Canvas by Thursday. That way you can make a final determination if you want to drop the class. But the take-home assignment, I'll probably give it to you on Wednesday, but it won't be due till following week. Yeah.